standard video that I make. The video, I just say it again since it didn't start recording until moments ago. The video that I'm rolling right now is the standard video that I process after class is over with. It's asynchronous to what I'm doing on Slack. I'm not or what I'm doing on Zoom, and I'm not doing anything on Zoom with its systems for recording and so on and so forth, because I don't want to learn a new thing and have to go through issues only to come back to my system that I've used a long time. So you can share your microphone at any time if you want to say something, and if you want to acknowledge that you're present. Caleb, I still haven't heard from you yet. Are you listening or too far away?
No, I can hear you if you can hear me. I don't know if the mic is actually coming through. Okay, good.
No, your mic is very loud. So there's 3 of you, and I guess everybody can see as much as I can. I'm already sharing my screen, so if that becomes an issue, let me know, because one of the things that happened, and this takes me back 2 years, well, yeah, over 2 years now, in spring of 2020, when I was lecturing away, when we first had to start all this stuff with COVID. My lecturing was going along smoothly, my recording was going along, and then people would have to tell me that I dropped off the video call because I didn't have any idea that had just happened. I was using an earlier system. So, okay, I'm going to start by just, if you're familiar with this little guy right here, some of you are, some of you aren't. This is why we're here today. Not because I'm feeling bad right now, but because when I started feeling like I was getting sick the end of last week, I started testing and using the rapid test here, and on Sunday is when it showed that I was positive, and then this was one that I ran yesterday just to see if I'm staying positive, which I expect I will for a while. Although I'm feeling better daily and did not have a hard time except for over the weekend. Parts of Saturday and Sunday were I wasn't feeling too good at all. But then things started to clear up. I don't want to have to go through this again, but I don't know. Some of you have probably done it more than once, or at least I know people at my church that have gone through it multiple times now. So it has set me back in grading, and I expected that it would. I just felt so bad. I didn't want to try to focus on anything over the weekend, and I'm finding that my hours I can spend are, I'm finding that it's better to go to bed a little bit early right now, because it helps me recharge, get more time to recharge. So I don't have the grading completed, but I do have things in progress. I could push back the set number 3. I just haven't done that. I finished that yesterday, and I was grading the exams yesterday, and then decided to just go to bed rather than stay up late to finish that. I've got plenty of things to talk about. This chapter that we're moving into right now is, with the sampling theory, is fabulous. I mean, there's so many things to learn about sampling theory and apply it to just generic signal processing and also to communications type signal processing, and we'll have examples coming along with all of those things. And I'm going to do some demoing today to help motivate a really fundamental concept used in software-defined radio, and that's undersampling, and how you can take advantage of some properties of sampling bandpass signals where you don't have to satisfy the Nyquist sampling theorem. You just have to figure out how to make things fit in, and I'll show you what I mean by fit in here a little bit later. So I'm going to switch over to, I don't have anything new on the website. I have the zip package that got finalized after class last week for project 1. I think I made a slight tweak to it with some file names that had changed, or function names that had changed. My co-author on Modern DSP went through and refined some of the Python function naming I was using. It's called making things more Pythonic, so he changed some things from uppercase to lowercase, and that keeps haunting me because I don't catch all that stuff. But at any rate, I'm going to flip over to here so we can start talking about sampling theory, and I'm going to see how I can minimize my sidebar screen from Zoom so I can see more of my screen. In the meantime, though, I am going to give you an update on, and that's in a bad spot too. I'm going to give you an update on the grading that I have done, and I know some of you are probably really anxious to know what I'm going to do with the exam and how that grading has gone. So the first thing I want to just show you is that I did finish grading set number 3. It was worth 175 points, and this is just showing you what the histogram is on those 175 points. And then if I merge that data into sets 1 and 2 already, I come up and then normalize that to 100%. This is where that class standing is. So there are people doing really good, there are people not doing so good, and I just keep seeing the same kinds of things when I'm grading. People that do effort and lots of effort, and those that aren't putting in as much effort, or at least certainly not getting things figured out as nicely as I hope for. As a result of this last assignment being merged in, there's now only one person that's got over 100% due to the bonus problems, but that's not a big deal. You can see there's 3 people in the 90s and 1 person just over 100, and then the scattering on the rest of them. Because I haven't made a lot of progress on grading the exam, I decided I'd do something I've never done before, though I'd at least give you a progress report. And this shows you on the first exam problem. And let's just go look at this so you know which problem we're talking about. Again, I'm messing around with my little bar that's part of Zoom because it's in my way. This was problem number 1. It was periodic sequences. It was something we talked about in the first serious lecture of the math, and I think it caught almost everybody by surprise. People didn't do really well in this problem. This is one that I've graded already. But just to review what the fundamental thing that goes on, pun intended, I guess, if I can get my pen to start working. When you are working with a periodic signal like a sine wave or a cosine wave, if it's going to be a periodic sequence, it's all about finding an integer value where it repeats. And so we had 2 sinusoids here, so we have an omega 1 and omega 2, and if you remember, you factor out a 2 pi, and then you're looking for a ratio of integers, k1 over n1 and k2 over n2. And it's all about, the period then relates to n1 and n2. And for this particular problem, when I do that, this solution I'll probably put up pretty soon. I haven't done it yet, but it was available right after the exam last Wednesday. I just didn't post it. N1 and N2 both turn out to be 16, so that means the minimum period is 16. And to really drive that home, this was an after the fact study I did over in Python, where I set up the frequencies as given in the problem and just run it through, and then I did an overlay plot showing every period. That's what the red squares are, just making it obvious that when you have the superposition of those 2 sinusoids, you do get a sequence that is periodic, and you can see by the red squares there that is like a timing marker running along the sequence, showing you that it's repeating itself every 16. It's not 8, as one person thought. It is 16, and it's not some non-integer value either. For a sequence to be periodic, it has to be an integer, period. Not all sequences are periodic, though. That's one of the things we talked about. So I don't know if that brings on any questions, but that's over and done with. The other two parts of this problem were for a system T whose output is x of n plus n. The first question is stability. So the way this problem is stated, T is not said to be linear in time invariant, or LTI, so you cannot use any theorems that apply to LTI systems. You just have to go from the core definitions. And in this case, stability, you're just looking at, for a bounded input, is the output going to be bounded? And y of n magnitude is from the triangle inequality, which I talked about a few weeks ago. I'm having to reset my pen, so that's why it's taking me longer. We know that the magnitude of a sum is less than or equal to, or overbounded by, the sum of the magnitudes. And if we assume that Bluetooth works, oh, I have to keep resetting my pen. The maximum value of the input is bx, so then we just have this plus magnitude of n. And clearly, as n becomes large, that value is going to grow unbounded, so the output is unbounded, and the system is not stable. Causality is actually much easier, and a lot of people got this just by writing a statement similar to what I have. You can't use a theorem again, the LTI theorem. You just have to go by the definition. So you can see, though, that the input relies on the present, or the output relies on the present input only. That's just by inspection. You can see that y of n is equal to x of n, and then plus n. And the only troubling thing might be that there is a time-varying bias, and that's what you can think of n as being, but it has nothing to do with the input. It's like just a clock tick that's running in your system. It has nothing to do with the input x. So that ends up being true. So again, looking at the histogram on the first problem, then the first page of 20 points, yeah, it's not really good, but it is what it is, and I figured I could at least share that much with you right now. Some people did really close, and then others were just fumbling around a bunch. So that shows up in the distribution right here. I do expect things will get better towards the end of the exam, and if I would have had time this morning, I was going to try to grade in parallel one of the last 2 pages and just see how that comes out. As it stands now, though, I'll probably just continue to go from front to back, grading across each page, and then sweeping back up and starting over again. And that's kind of the way I grade exams, because I like to get a feel for what everybody's doing on each page before I move on to the next page, and that helps me figure out the best plan for partial credit. So I'll stop there and see if anybody has any questions before we jump over and get into Chapter 4's material. Go ahead and talk at me if you want to. Okay, I'm gonna proceed. I'm going to do a quick sanity check. Okay, I see Ryan has joined. Joe has joined. So you guys can unmute whenever you want to. I definitely don't need to have you show your faces. I'm showing mine just to let you know that I'm real, but I may even turn that off at some point. I'm hiding all the stuff right now, though. So I'd appreciate it if you're going to drop off and just leave, that you would just announce that you're leaving, so that way I won't feel at some point in my lecturing that I'm talking to nobody, because I want to know that difference, that nobody's there, which has happened in the past. Okay, so just to review where we were when we were moving on into chapter 4 from last time, we have this process or flow of bringing an analog signal in, sampling it, A to D converting it, and then at the heart of the matter here is our DSP processor. And resetting my pen once again. What I just outlined in red, though, is pretty much what we've been doing on our own up to this point. We haven't taken into account sampling theory, but we've been working with processing blocks that process signal samples. When I say blocks, I mean like L-filter in Python and equivalency in Julia, or in those of you taking the lab, you've been processing signal samples in an interrupt service routine that brings samples in from the A to D and send samples out through the D to A. So we want to enhance our understanding of the front to back system by bringing in the blocks that we haven't talked about yet. So now we'll do this piece, and then we'll do that piece. And the very starting point is periodic sampling, and I'm going to be introducing the notation of the book so that you can understand how it does these things, and also how it factors into the homework problems, because the homework problems in the back of the book absolutely use the notation of the textbook. So I think one of the first lectures I just noted that parentheses are used for a continuous time signal, and to be add extra emphasis, a subscript C is put on there. So we're sampling it at multiples of the sampling period, capital T, and that gives us the sequence x of n. Once we have x of n, we don't have any direct relationship back to T anymore. It's just a sequence of numbers. The time aspect of it is a parameter that sits off to the side, but those sample values have already been taken. There's no changing them. The reciprocal of T is the sampling frequency or sampling rate, and we'll use that a lot in this chapter. So what does the book do in terms of how to represent the ideal sampler? They will show it as this block diagram on the left-hand side that shows that the input signal, continuous time signal, gets multiplied by a sampling waveform S of t, and the waveform that comes out of that is x sub s of t, and that's to mean that it's the sampled version of x of t, x sub c of t, but it's still in the continuous time domain. So it has to get converted from an impulse train sampled signal in the continuous time domain to a discrete time sequence. And the mathematical version of that is kind of abstract. It doesn't call it a to D converter. The book calls it a continuous to discrete converter, C to D. The A to D part is the reality part, and from the math modeling standpoint, the book just wants to call it a C to D and make it be kind of mysterious how the conversion takes place. So the equivalent block diagram is what's on the right-hand side, where it just says C to D, continuous time waveform enters it, and then there's an arrow on the bottom usually that comes up and either puts in T, or equivalently it might just be Fs, which is 1 over T. That's perfectly fair. Just some means of indicating to the reader what the sampling rate is or the sample spacing is. So what does the sample waveform look like? It just looks like an impulse train. And the reason why it's written as a multiplier in there, you could also think of it as a switch that's opening and closing every cap t seconds, and it just lets through one value of the input at that sampling instant, and that's what the idea of the delta sequence is just letting a sample occur. And when you write that out down below here, it becomes the product then. And if you look at it expanded out with the impulse train, you can see that the only thing that comes out of as xs of t is x sub c at sample instance n times capital T, because the delta function is 0 everywhere except at the point that it turns on. And it turns on at all multiples of n times capital T. So this is what's going on inside that block diagram. On the left-hand side, x sub s is the impulse train sampled version of the analog input. And then on the right-hand side, it gets converted to a sequence of numbers. And that's, in reality, is the operation of the A to D converter. You feed it analog input, you have a sampling clock set up, and it goes through a conversion cycle, and then there's a sequence of signed integers, let's say, in our instance on the DSP board in the lab. Signed integers come streaming out every clock cycle. Another sample comes out. To get the understanding of sampling theory to really take a hold, we have to flip over to the frequency domain. So now we're going to do that by taking the Fourier transform of S of t, and that's really the primary motivation for wanting to do this model over here. We have S of t, we have x of S of t, and then we'll have to do some mathematical refactoring to relate that to the spectrum of x of n. So fundamentally we're going to have over here I guess I shouldn't put j in there, I should just put omega. The book likes to use omega domain transform, so they'll use capital omega. And then over here, we're going to have the discrete time Fourier transform, x of e to the j omega. So what has to be figured out is how those two are related to each other. The continuous time signals Fourier transform and the discrete time signals Fourier transform, how are those related? As an intermediary step, x sub s of t is what we're going to be looking at to start with. So we're going to have x of s of omega. As soon as we adopt this result right here, which is one of the theorems of continuous time Fourier transforms. So remember, I hinted at this weeks and weeks ago that we would need the continuous time Fourier transform. So the next page of the notes is just the review of the Fourier transforms. And I guess my brain wigged out there. I am using x of j of omega. So I could change this back. It's really not that big of a deal. Just to add the j in there for the emphasis that it is complex. But at any rate, this is the continuous time Fourier transform in the capital omega domain. And capital omega is used to keep the frequency axis in the analog continuous time domain distinct from the discrete time domain where we use little omega. And that's the book's way of keeping the two of them squared up. It might have been like in 2610, you might have seen omega hat and omega. In this book, it's capital omega and little omega, which I happen to like better. Putting the hat or the circumflex on top of the omega is just an added complexity in writing and is something that sometimes gets too hard to read and confusing. And I'm already confused enough when I'm grading homework papers and I can't figure out the scribbling at times, so don't have to worry about that. It'll be capital omega or it will be little omega. The only thing that remains is what is F in hertz, and sometimes this is my preference to use capital F for the analog frequency in hertz and use lowercase f for the discrete time frequency in samples per or hertz per sample. More on that later though as things unfold. So forward and inverse transforms, not symmetrical. There's a 1 over 2 pi in the inverse transform. What's important to us right now are some properties, some theorems that are useful. So I've got some of those theorems right here and properties written out in this table. This is pretty much all we need, maybe a little bit more than what we need, but it'll be useful also in some of the homework problems too. So the one we're homing in on right now is you want to take advantage of multiplication in the time domain becomes convolution in the frequency domain. And then we want to recognize also this property, that if you have an impulse train in the continuous time domain, you get an impulse train in the continuous frequency domain. So both of those are useful right here. So we have to go after, first off, what is the spectrum of the ideal sampling waveform, which is right up in here. It is just an impulse train in the frequency domain. And then secondly, because we're forming the sampled signal as the product of the continuous time signal and the ideal sampling waveform, we use the convolution theorem, or multiplication theorem, I mean, which tells us it's convolution in the frequency domain. So we have, from that theorem, we have the 1 over 2 pi which is just part of the theorem. Yeah. And then we have the convolution of the continuous time signal spectrum and the spectrum of the impulse train getting convolved together. But because of the fact that we have a delta function in here, the delta function convolution is very easy. It just replicates x sub c of j omega, and that's why we have just the spectrum of the continuous time signal replicated at multiples of the sampling frequency, and those two things cancel, but we do net out a 1 over capital T out in front, and that's something that'll carry through in all of the plotting and other things you do in homework problems, that ideal sampling produces in the spectrum a scaling of 1 over T on xs of j omega. And soon we're going to be relating that to x of e to the j omega in the discrete time domain. So that's fundamentally the spectral result when you sample a continuous time analog signal. And the big deal about all of that is that if the analog signal has got a band-limited spectrum, like I'm showing here, a triangle shape, and we sample it at a rate where omega sub s, the sampling rate, which is 2 pi times fs, or 2 pi over capital T. And if we sample it at a rate where, in radians per sample, or radians per hertz, I mean, is greater than twice the highest frequency, which is omega n, then we get, this is our sampled signal spectrum, and we're all happy because we can reconstruct, and that's the next big thing to talk about. What does it mean to reconstruct? We can reconstruct and get back to our original spectrum because it's isolated from all the other spectral translates that show up as a result of sampling theory. I'm going to do a demo of this in a second. If we don't obey sampling theory, which says we have to sample at greater than twice the highest frequency, then we'll have what's known as aliasing. And aliasing is a permanent damaging effect. We have spectra overlaying each other, the translates overlay each other, and in general you cannot get information, the desired information, back again because it's been corrupted by the aliased component. In particular, if you're looking right in here, the tails of the triangle from above and below are overlapping inside, and now they're corrupting the original baseband spectrum that's centered on 0 hertz. And that's the nature of aliasing. It's a permanent damage thing. If you knew exactly what the signals were, then you could excise that, but in general, if you don't know that, and you generally don't know that a priori, if your speech gets aliased, it just sounds poor. It may be unintelligible, actually. So a little bit on what does it mean to recover. Recovery just means that I'm going to process the waveform with a low-pass recovery filter. So I can take my sampled waveform x of s of t and go through this series of operations here, sample it. The spectrum now becomes the replicas of the input signal spectrum as a result of ideal sampling. So that's step 1. Process it through an anti-aliasing or recovery low-pass filter. I mean, that's step 2. I didn't mean to say anti-aliasing because that's another thing to talk about. And then observe that the output spectrum is just the signal that we started with and would like to get back at some point. And this equation is just the essence of how the cutoff frequency of the reconstruction filter has to be chosen. It has to be chosen greater than the bandwidth of the signal, but less than omega s minus omega n, to avoid taking part of the spectrum away. So it just has to fit in this interval right here to avoid letting some of the aliased or some of the higher frequency come in and not clipping off any of the desired baseband signal. And there's various examples in the notes here and in the book of, say, working with a sinusoid, choosing the sampling rate to be greater than 2 times omega naught here, and then looking at how the recovery can take place. There's homework problems along these same lines, and frequently what you're doing in the homework problem is you're drawing pictures just like this. I think I eventually will have, I'm just trying to dial ahead and remember where this idea first occurs. Right now I'm making everything look pretty compact, so just because the way I laid out the notes pages. The way I generally work things out, though, for homework is to stack all these things. So I would, if I was doing a homework page, I would have this plot stacked on top of this plot, and then I would have that stacked on top of this plot, and then the fourth plot would be something like that. So you would just see this on the page vertically. So you'd see the action of, first off, the original spectrum, the sampled signal spectrum, and then the action of, in this case, an analog reconstruction filter, and then finally the recovered spectrum. Other intermediate plots might show up depending upon other signal processing operations going on in the system, but I drew these pictures compactly and then using arrows. Generally though, when I write solutions out to homework, it's not like that at all. And maybe I can actually show that if I can get my, I'm just going to grab an example out of here, and I'm going to turn my camera view back on again. So this is part C of problem 415, and I'm just giving you an idea of how that kind of gets demonstrated, where I start off with the original input signal, it gets sampled, so it has images of the spectrum, and then it has some processing that's going on in the third plot there, and then the final result is at the bottom. So I do a lot of that, and the book talks that way also. This is an earlier part of that same problem where it's sinusoids that are going in. Then images occur when it gets sampled, and then there's some filtering, and then finally the recovery operation. So things like that are a good way to explain what you're doing in these homework problems. That way you can just follow it through. And on the next exam, you'll have things like that too. I mean, the next exam will be the take-home exam leading into the Thanksgiving vacation week. So what I want to do right now, before we move on, well, I'll just quote here Nyquist sampling theorem. It says that if our desired signal is band limited, then we can always recover it from samples. My throat's starting to get dry and scratchy, which I expected. So I have some cough drops. I'm going to try to keep it going. If this fails, I may have to quit. I don't know. We'll see what happens. For those of you that have had COVID before, maybe you had a really dry throat. I've heard of it. I've never had it before, so I'm just living it for the first time. Okay, so the Nyquist sampling theorem says we have to sample with omega s greater than twice the highest frequency. And my eyes are watering too. Omega n is the Nyquist frequency, and 2 omega n is called the Nyquist rate. Those are just the definitions that go along with this. Next, mathematically, we want to bring in or tie in x of e to the j omega with x sub c of j omega. This is vitally important because it's going to allow the continuous time signal spectrum to be related to the spectrum in the discrete time domain. Cough drop is starting to work, but it's not great. Next thing I'm going to do is show you some demos. This is from Jupyter notebook, which is going to get reposted. It's currently up there, but this version is going to be a little bit improved in some ways. I have some tools in Python. In particular, this was written originally for ECE 2610. It's a function called principal alias. It's a very simple function. It does this operation right up here. Seeing if water will help me now. And it gives you the principal alias frequency from a given input frequency and a given sampling rate. And from this plot right here, you can see that if I use this to plot the principal alias frequency versus the input frequency, you can just see how aliasing does take over. And I can give an example down here of that. And I'm going to use another app to demo that. But here, I just said if I'm sampling at 20 kilohertz, and I bring in 3 signals, 2 hertz, 18, and 22. Those 3 frequencies are all identical. The fundamental or principal alias is at 2 hertz. 18 sits 2 hertz below the sampling rate. 22 sits 2 hertz above. So those also fold on down to 2 hertz. And this picture just shows the plotting of all 3 of those signals, where the sampling rate is chosen to be 20. Throat is extremely annoying right now. I don't feel bad, except I can't talk because it's wearing it's wearing out on me. But those are all identical. So now what I'm going to do is I'm going to just run a couple of apps, and all of these apps are available on the website. They were written in Zojo, the same language I use for developing developing the GUI slider app. So the first one is called Sampled Sine. And I wish I could talk without this fade out. It's like somebody's got a little brush down in my throat and they're just wiggling it around trying to annoy me like crazy. So here's an example of, in this case, I'm assuming I have a continuous time sinusoid, and a sampled version of this is being made as I'm going to change the frequency of the sinusoid from 0 to 1 hertz. So this slider up here, I can control the frequency of the sinusoid. The sampling rate is always at 1 hertz. So when I'm at a low input sinusoid frequency, I get many samples per cycle, like you see here. As I increase the sinusoid's frequency towards 1 hertz, I start seeing less samples per cycle. And as I move my way up towards the midpoint here, that's a very special location. So if somebody wants to chime in, I'd appreciate it. Give me more time to rest my voice. What frequency am I at right now for my input sinusoid relative to 1 hertz sampling? So I'm at half a sample per second, or 0.5. So I'm seeing only 2 samples per cycle. You can see that right in here. And if I go like this, now I'm starting to alias because my sampling rate is not greater than twice my input frequency. And it's not really obvious that I'm aliasing, but as I move this up, there's an optical illusion that takes place in front of your eyes. Eventually you start seeing that aliased frequency present, and it occurs differently for everybody depending upon how your eyes are trained. But as I move this up higher and higher, I'm starting to see it right now. It's a little bit more obvious probably right here. But if I go up higher and higher, now it should be really obvious. The blue dots are following a much lower frequency, right? It should be very obvious there. If I click this button over here, now I'm going to display the alias frequency. So when I reach the folding frequency, or fs/2 for my input, which is right there, now it's going to show the output as coming down in frequency because I'm looking at what the action of aliasing. I'm looking at the principal alias. Another interesting thing that I like about this plot, and I created this exactly for this class to demo stuff. If I move back up to the exact folding frequency I was at before, so my input is at 1/2 hertz, I'm sampling at 1 hertz, I'm getting 2 samples per cycle. If the phase of the sinusoid is now allowed to modify, what can happen is that I got to get this set up a little bit nicer. I'm trying to get this exactly at 1/2. Then I move the phase and like that. So if the signal phases in the wrong way and I'm trying to sample right at the folding frequency, my signal is right at the folding frequency, I can actually get nothing out of the sampler just because of the fact that the phase of the sinusoid puts all the samples at 0. Obviously, in a real system, having a phenomenon like this occur is very unusual because generally the sampling rate clock and the signal are asynchronous, one of them sliding past the other. So over time you would see a small beat note or frequency difference in the samples, but you would never see them hold at 0 value because the clock oscillators will drift relative to one another. And for those of you in the lab, you got to see a little bit of this. I think when I was observing you do some experiments with bringing the input sinusoid frequency up to the folding frequency, and you were watching the output on the scope through the D to A converter. If anybody wants to just say, yes, I remember that, that would be helpful to me, but otherwise my throat's starting to recover a little bit. Any questions on this? If not, I'm going to move on to another demo. If you want to get a hold of this app, though, it's on the website. It's a Windows app, and it's got a folder of library stuff in it, and then I'm going to move on to another app called Sampling Theory app next. And these other 2 apps we'll be looking at later. So I'm going to close this one down. And I'm going to bring up Sampling Theory. So this one is going to allow us to look forward and also look backward. So I'm starting out with a low-pass signal spectrum, and what I'm allowed to do with the slider down below here is vary the frequency of the sampling rate relative to the bandwidth. So if the sampling rate is exactly 2 times the bandwidth of the signal, then I can see I'm just sampling fast enough to avoid aliasing. I'd have a pretty hard time recovering the signal because the fact that there's no frequency to have a transition band in here for my filter. So I typically would end up sampling faster so that I could recover the translate at 0 and ignore those that get created as a result of sampling. If on the other hand, the sampling rate is less than twice the highest frequency, then I'm getting all this aliasing impingement from the upper frequency translates on top of the blue baseband translate. Not good, right? Now the next little game to play, though, is suppose we have a bandpass signal, and I've got two different types of bandpass signals, but I'm going to pick the narrower of the two. So here we have a bandpass signal that could be like a communication signal, a radio frequency signal. It's got an upper frequency band and a lower frequency band. And then we're sampling. Right now we're at 2.5 times the sampling rate. I'll drop the sampling rate down, and now we're just at the Nyquist rate of twice the upper frequency. But because this is a bandpass signal, there's all this spectrum that's empty in the middle. And no, I don't want to do that. That's bad aliasing. But if I bring my sampling rate down, I'm now sampling below the Nyquist low-pass sampling rate, but I could recover this signal from the sampled signal using a bandpass filter, let's say. Or in a radio application, RF sampling theory application, maybe I don't even care about the blue signal. I'm fine recovering it from the translates that are in the middle at using lower frequency electronics. So drop the sampling rate down even more, and I don't know if you're seeing how I'm seeing, but hey, I can drop the sampling rate down an awful lot as long as I can keep this image clean and I don't have anything over any of these spectral translates overlapping each other. This is just a different version. This has got a wider bandwidth, so I can't bring the sampling rate down as much to recover the signal. This is the principle of undersampling now, and as it's utilized in software-defined radio. Does that bring up any questions from anybody? This is, to me, this is very, very exciting, and it's used all the time in software-defined radio applications. The fact that you can undersample. If there are no questions, I'm going to move on. And I'm going to shut this app down, and I'm going to go back over to the notes. I do have some functions for simulating bandpass sampling theory stuff in the Jupyter Notebook. I'm going to not refer to that right now. It depends on which homework problems I have assigned this semester, whether or not you may want to play with those functions to help figure out a problem solution. A lot of what goes on in sampling theory, though, is to be able to visualize the spectrum, and it can kind of overwhelm your brain trying to figure out where do all these spectral images go to when I change the sampling rate, or if the signal spectrum changes. Do they overlap? Where do they move to? And I find it helpful to use software tools in particular to visualize what's going on in the frequency domain, because otherwise you have a hard time drawing this rapidly on a piece of paper such that it makes sense to you. It's pretty nice to have computer assistance here. So moving forward, we want to relate x of e to the j omega with x sub c of j omega. Why is that even? Why do we even care about that? Well, you have to go back to the original block diagram and see that both of these signals are present. We have, let's just stay over on this side if I can get my pen to reconnect. That's our analog signal coming in, and we're going to come out with it over here. We want to not be talking about this spectrum. That's an intermediate spectrum. We've been using that spectrum to get understanding and develop the frequency domain analysis right here, x sub s of j omega. But that's an interior part of the model. We want to think in terms of the top level, and the top level has xc of t and x of n in the sequence domain. So we need to take this step, and that's what this part of the notes is about, drawing the connection between the two. The stepping stone is going to be xs of j omega, but what we want to end up with, and what we're only going to really focus on from here on out, is xc goes to x of e to the j omega. So the first observation is to say that in terms of x of s of j omega, we could get there, we could get its Fourier transform by just viewing it in terms of this Fourier transform pair, where we have a time-shifted sample on the time axes, and we have this theorem that says that's a times e to the minus j omega t naught. That's the result of a time delay in parts of linear phase onto a signal. So we can go ahead and Fourier transform all of the samples of the analog signal using the time delay theorem, and that'll give us x of s of j omega. And then we can notice that x of n is just the direct samples of the original analog input. My pen is constantly disconnecting, so I'm having to mess with it. X of n, and this is just going to be a discrete time Fourier transform idea, where we're just saying, okay, we have a sequence here, and I wish this would stay connected. That, and then view this as little omega, and that's what I'm showing down in here. So x of s of j omega is also equal to x of e to the j omega, with omega replaced by little omega replaced by capital omega t. So this is the stepping stone that we are needing to try to relate Fourier transforms from the continuous time domain and the discrete time domain. Hold on a second. We have another puppy in the house, and I think she wants to go outside, but I'm not positive. I want to introduce her to the class, though. Can you hand her to me for a second?
Introduce him.
Him, yeah. It's a he. This is Rocket, and he is a Whippet puppy, and goes along with our other dog. So our other dog, Ember, which is a Manchester Terrier, almost a year old now has a playmate. But this is typical of puppies, right? They need to go outside, because if not, there's an accident. And she was chewing at my foot, so he, yeah.
That's a good sign.
And if you've ever raised dogs before, you know it happens really fast. If you don't pay attention, the next thing you know, something's happening. Okay, I'm glad I have a bag of cough drops. I've recovered. I've gotten back to square zero again. I just have to stay ahead of it somehow or another. So with this stepping stone, basically it comes down to this omega. Little omega is capital omega times t, the sampling period. And of course, if we write this out another way, if I get my pen going again. If that was, say, 2 pi times f, and then t is fs, is 1 over fs, I mean. So little omega, another way of thinking of it, is as 2 pi times f in hertz over the sampling frequency. fs in hertz. So that's the substitution that ends up being made. So this blue boxed equation is a fundamental result. It's just telling us how we take the analog signal that's coming in and how we relate it to what we see in the discrete time domain, x of e to the j omega. And we see the translates of the analog signal, all at multiples, shifted by 2 pi. I didn't draw that quite right. Two pi k over fs, so we're shifting at multiples of fs again, and then we're putting the 1 over t scale factor that was on there from the Fourier transform theorem in the very beginning. So what I like to do frequently when I'm drawing that is I like to draw this picture right here. Where if I'm looking at the omega axis, this would be omega sub s. That's omega s over 2, but then I can bring in little omega if I want to. Little omega is, remember, this relationship, so this becomes pi. This becomes 2 pi. And I could draw a third axis in here if I wanted to too. So if I wanted to put up frequency in hertz, this would be fs over 2. That would be fs, and that would be 0. So all the axes just stack on top of each other to quickly see the relationship between the two. And my personal favorites would be that and that, just because I like working in hertz. And of course, in the discrete time domain, we have to think about omega. But we could also use little f to be the normalized frequency in radians per sample. So yeah, if you want me to make the drawing more confusing, I could put little f in here, not capital F, and then this would be 0, 1/2, and 1, if you wanted to do that. I don't know if that's driving you crazy to see how those different things, but it's nice to be able to be flexible and understand how things are related to each other. So the next topic would be reconstruction of band-limited signals from its samples. We've already shown that a reconstruction filter just needs to be a low-pass filter that we can fit between the folding frequency and the highest frequency of the signal. And we can actually write out what that needs to look like in the time domain. We're going to have to go backwards now and reconstruct. We want to get back to our sampled signal from the samples. So we're going to convert back to the continuous time domain, but we want to put in a reconstruction filter, and that will be the impulse response of some low-pass filter. So x of r is x of s convolved with a low-pass filter, and that will just be the operation of putting the impulse response of the low-pass filter in the continuous time domain and weighting it by the samples of the discrete time domain signal. And this would be on the back end of our system when we go through the D to A part of the system. So what should this filter look like? Well, the ideal reconstruction filter is an ideal low-pass filter. In the book in particular says it will have a gain of t, and the cutoff frequency omega sub c just has to lie between omega n and the folding frequency. And that means it has a sinc function for its impulse response, because that's the inverse Fourier transform of a rectangle. Why do I know that? I'm just going to fly back up here for a second. That was in our review table, right over here. If we have a rectangle in the frequency domain, we get a sinc function in the time domain. This is continuous time Fourier transforms now, and I talked about that a little bit in here. Like, it's in the table, bottom line. So getting back our continuous time samples from the discrete time samples is just having an interpolation filter or this sinc function running. And if we set the sinc function exactly at the folding frequency, then it specializes to the case given here, and that becomes what the book calls the ideal discrete to continuous function. It consists of converting from impulse train back to continuous time domain, in other words, going back to get the sampled waveform, and then having the ideal reconstruction filter being the sinc function. So I have a picture of that here. The analog signal comes along and you sample it with an impulse train. Then you want to get the signal back again. It's placing a sinc function scaled by the amplitude of the sample at each of the time samples, and that's the lower picture here. See if the pen will go again. Then you can see at any sampling instant I pick, I'm just going to add up all the contributions from the sinc functions from the samples that come before and after, and that brings me back up to my original signal. Now we can pause here for a second. I used the word before and after. Is it possible to build a filter that can use future values to help get the output again? And that would be a non-causal filtering operation, right? So no, we can't really do that. When I was first learning more about digital scopes, and I taught a class on FFT applications to what was Hewlett-Packard, later became Agilent, and of course now is Keysight. One of the things that they were talking to me about is how in their digital scopes they take the discrete time values to put them on the display, not to send them back out again, but just so the user of a digital scope can see it on the screen. They were using some reconstruction filtering for the display, and they have to use some sort of an interpolating function to do that. But they can't violate causality. But this still is a useful picture, even though this assumes a sinc function which has infinite tails. But for a data display application, you could get away with this, right? Because you'd have all the data, and then you'd put up the display, and then you could add the signals like I'm showing here, add them up to get the reconstruction. So this is this picture right here. D to C with a T coming up in the bottom. So this is used in the book, in the homework section in particular. So this pairs up with the C to D, continuous to discrete, and the arrow coming up from the bottom, like I said before, is either sample spacing T or Fs, which would be 1 over T. Any questions on this? Okay, I'm going to keep moving. It's making me... Is there a question, or am I just hearing some feedback? I'm just going to go check and see who's on right now. Okay, Jack, you joined silently. If I was in class today, and a lot of me said I wanted to be in class because I don't really like doing this. I never thought I'd have to do this before I was officially gone from teaching, but here I am, I'm having to do it again. I never thought this was a very good way to go. It's acceptable, but not great. So the reason why I didn't come to class today is that I have to hurdle the rules of the university right now, and it has to do with my still testing positive, but eventually I have to be able to return, and I'm going to have to read the rules again and again. And some of you have been in this situation already, so it's just frustrating right now. It turns your life upside down, for sure. My wife was having a procedure at the end of the week at the hospital. That went away. Just a lot of things are kind of gone away for the time being because of me having the infection. Okay, discrete time signal processing and continuous time signals. This is a little section that's thrown in the book, which I just want to mention briefly. You're seeing what you're seeing, it's really in the book. Why would I want to do this? Why would I want to process a discrete time signal in the continuous time domain? It's just simply saying we could do this if we wanted to. So we could start, well, wait a minute, I'm getting ahead of myself. That is what I wanted to do. There's another example down here that I haven't gotten to yet. It's a whole section in the book. Maybe that, or continuous time processing of discrete time signals. This is, I'll just highlight that. Why would you want to do that? I'll come back to that later. So I'm now going to look at, fundamentally, this is the streamlined version of what we started with and what's in the first page of the notes for chapter 4. Now with our new notation, though, we have continuous to discrete is just our abstracted view of the whole front end. The continuous to discrete converter. And by the way, if I didn't mention it before, never mind. There is no anti-aliasing filter in this continuous to discrete converter, so we have to watch out. This will accept signals and they will alias, but this does abstract away the details of the A to D converter and the finite precision arithmetic effects of a real A to D converter. This is our familiar most of the time LTI system, and then the C to D is just the abstraction of the D to A converter, which, remember that this will have a reconstruction filter in it that has a gain of T to make up for the 1 over T that happens in sampling theory. So I guess I should back up on that right now and just review that. This will be important when you work homework problems. So when you are going to go continuous to discrete, or discrete back to continuous, you do have this ideal analog reconstruction filter, but notice the capital T is on that frequency response, so it's got a gain of T in this resolves the 1 over T in sampling. So if the signal comes in as 1 over T, now it's going to get scaled by capital T when it gets reconstructed back to analog again. So that makes it come out normalized. So I brought all that up because I just wanted to point out that this, I'm drawing this with my mouse for now. That has a gain in it. It's not unity gain. So now we can work this all the way through, and we can just see what do we have when we have this end-to-end C to D, H of E to the j omega, D to C system. So this is kind of like a dream that it's actually the hardware system that those of you taking the lab have been playing with for a few weeks now. So you have such a system with your FM4 board. So if we think about the signal coming in, we're sampling it to get our sequence X of n, which is right up in here. Then we want to view it in the frequency domain. We can see it's going to be, this is going to be the spectrum of that sequence, X of e to the j omega, taking on translates of the input signal spectrum at multiples of the sampling rate. And then when we fire that signal back through to the output, suppose in this case, I don't say it right here, but I mean to say it. Suppose the output is exactly the input, the direct through path, then we can jump down and look at what the output signal spectrum is. It will be the output signal with sync in there to interpolate it back again, and in the frequency domain it will be picking up this gain of T in the reconstruction filter, but the reconstructed signal Y of e to the j omega in this case will be X of j, X sub C of j omega. Under that situation there. So it comes back around, and the spectrum, of course, is limited. The spectrum is only going to apply if we're in the sampling rate bandwidth from minus fs over 2 to plus fs over 2, or plus and minus pi over t for the sampling rate. Just always remember that when we're working with our sampled systems, we have to, in our math model at least, we have f over here so our usable bandwidth is between minus fs over 2 and plus fs over 2. Reconstruction filter guarantees that. Reconstruction filter does not guarantee, though, that a signal cannot arrive at the input and alias, still make it through the discrete time system, and come back out over here at a different frequency. Those are interesting things that the homework problems look at. Okay, so now if we suppose the system is LTI in the middle, so we can multiply to get the spectrum. And I was kind of hedging on that because I was starting to get excited over here by just saying y is equal to x, but now we're going to say signal is LTI, so, or the system is LTI, so the signal can process from input to the reconstructed output through the response of the system with little omega replaced by cap omega t, and then we can finally get the output spectrum. So I'm just going to do this. I'm hearing interesting sounds from somebody's microphone. At any rate, nobody wants to admit to it, though. I don't know where it came from. We go back and forth from little omega to capital omega times t, and then can come back again. So if I want to make substitutions in one direction or the other, I can do that. And that's what's going on right here. So I can get the frequency spectrum as the input signal spectrum times the digital filters spectrum with little omega replaced by cap omega times t. And I can see then the action of the filtering in the discrete time domain and how it shows up in the continuous time domain. So the book calls this the effective frequency response, which is valid only on the interval of minus fs over 2 to plus fs over 2. And this is why DSP is what it is. Because we can do this, we therefore want to do it and have all the programmability of our system be in the discrete time domain. If we didn't care about that, we wouldn't be doing DSP. So is everybody good by that? So more examples in here. This is just, suppose we want to build an ideal low-pass filter with cutoff omega c. So here's our effective design. We'd like to have the cutoff frequency be in the analog domain, be at plus and minus capital omega c. But we build up our continuous to discrete h of e to the j omega times discrete to continuous system so that we can implement that filter in the discrete time domain. So here I'm just showing the input signal. It's when it's sampled, it's got its replicas, and little omega axis, just for completeness, is in here. And now we proceed to send that sampled signal through a digital filter that has a cutoff, digital filter frequency cutoff of little omega c, and that would be equivalent to big omega c being equal to omega c over t, just by rearranging the math there. And the net result, if we carry that through, all the way through to the output after the reconstruction, that we get the filtered signal like we were expecting to get. So we built a a discrete time filter we built the effect of an analog filter in the discrete time domain. And if we're willing to, change the sampling rate, let's say we can actually build a variable frequency cutoff filter without changing the filter, just changing the sampling rate. And that's talked about in another little example here, I think. Well, it's kind of talked about right here. This is something that in the lab you get an opportunity to see if you want to give it a try. If you design a filter to operate at a particular sampling rate and then decide to run your board at a different sampling rate, the filter is still being a filter, but it will not have the same cutoff frequency because it'll it'll rescale with t or fs, which is 1 over t. So a set of filter coefficients will work as desired at the designed for sampling rate, but then if you run it in the system at a different sampling rate, it'll just remap that to a different frequency. Okay, I'm looking at the clock. I've got another example that is kind of motivated by the one I already showed you quickly in the Jupyter notebook, but it didn't have as much detail as this. I guess I'm going to finish this, and then before I do this, I want to find out what you want to do with the break. I'm sitting down. My throat's going up and down. It's not going to get better no matter how long I try to keep nursing it. The only way it's going to get better is for me to stop and not do it anymore. So my preference would be to just keep going and then quit early. But if you want the break, we can certainly do it. I'd like to have some feedback on that right now before I do this one last example.
I don't mind either way.
Okay.
Yeah, I'd say keep keep going if you can keep talking for now.
Okay. Anybody else? Okay. That's what I'm going to go for then. I'm going to stand up for a second though. I do get tired of sitting, but I can always stand up and talk if I have to. Okay, so this example is not from our book, but it's one that I had found in another book years ago. It's just looking at what happens with aliasing, or what happens when you have aliasing and you are considering the design of a system in the discrete time domain that has this magnitude response and this phase response. So we've got three different signals that are going to be applied to the system that is the system we've been talking about here. Get back to the block diagram if I can. This system right here, except I'm going to now remove what I had on here before. So it's this system right here, and I'm describing the response of the discrete time system is given in this example. So it's got this magnitude and this phase. And now we're going to subject the system to three different inputs. And unlike the FM4 board for the lab that has anti-aliasing filters built into it, this model does not have an anti-aliasing filter, so these three signals are going to get acted upon differently. The sampling rate is, oops, see if this will work for me, 5 samples per second, and I'm going to be putting in an input at 1, 6, and 4 hertz. So quickly thinking about that, your brain should go, if I'm sampling at 5 hertz, my folding frequency is 2.5 hertz. So as long as my input doesn't exceed 2.5 hertz, I have no aliasing and everything is going to be kind of normal-like for making this filter look like an analog low-pass filter. But is that true in this case? Only for the 1 hertz input. The 6 hertz input is definitely above Fs over 2, and as is the 4 hertz input. And in fact, thinking about the principal alias, all of the signals land at the same spot. 6 hertz relative to a 5 hertz sampling rate is a 1 hertz principal alias. 4 hertz sampling at 5 hertz is also has a principal alias of 1 hertz. So they're all identical, but not quite. Because I'm going to assume a sine right here, and sine is an odd function, x1 of n and x2 of n, which are the 1 and 6 hertz signals, will be, those samples will be identical, but when I sample at 4 hertz, because of the fact that I'm now 1 hertz below the sampling rate, the sine function creates a sine change in x3. And that's not quite illustrated in this picture, but it is in what I have in Python. Actually, yeah, it's over here. If you look out all the way through the system, the 1 hertz signal comes out filtered and phase shifted. The 6 hertz signal comes in phase shifted and attenuated. The 4 hertz signal gets flipped in sine because of the fact that the input signal is a sine wave and not a cosine wave. So these are the inputs. All their samples line up identically with the exception of, like I've already said, the sine change on the x3 signal, which I don't have shown in here. So all of these signals appear to be filtered and phase shifted according to the frequencies that they hit the system at. So if I look back up over to here, the 1 hertz signal is coming in, and as it enters into the digital filter, it picks up that amplitude, picks up that phase shift. The 6 hertz signal is right up over here on my omega axis. It picks up that amplitude, picks up that exact same phase shift, and then the 4 hertz signal is down over here. That's F3, picks up the exact same magnitude, because the magnitude responses are an even function of frequency, and the phase shift is the opposite in that case. But those get applied as they go through the system. The system doesn't know in the discrete time domain, it can't tell that it's aliased. It just sees everything lining in the Nyquist interval, 0 to fs over 2. So this is all the output is able to see, what lies in that fundamental interval, and that's why the picture over here just takes that into account, that's the action of that. And I'm pretty sure that's what I did over here in this example. If I didn't, no, I didn't do that. So let's do that for the fun of it. Here I brought in cosine at 2, 18, and 22. So these, and I'm sampling at 20 kilohertz. So let's just change this problem. Keep that part the same, but now what I'm going to do is I'm going to make this be a sine. That be a sine. And now run it. You guys aren't used to hearing a dog barking in the background, but all my graduate students always hear the dog in the background. So you're just hearing what seems totally normal for me to be doing a video call. It's just I'm not used to teaching class this way. So what happened here, is this making sense? 2 is in the Nyquist band. It lies less than 20. 18 is above, so I'm getting aliasing, but it lies below the sampling rate. So this one gets flipped in sine, because sine is an odd function. And then the 22 is 2 kilohertz above the sampling rate, so it doesn't get flipped. And those are the 3 outputs right there. Output for the 2, output for the 22 are matching, and then the output for the 18 is inverted, just because of the action of the cosine, or sine versus cosine. Since I'm going to post this later, I'm going to change this back again. Make sure I post the right version. Okay, it came back again. I don't think I have an actual example in here with a filter at this point, but I'm not really too worried about that myself. This is just a simple little example though, and I kind of like it because it just points out differences that will happen. If you're in the lab though, you won't really notice this, because you don't notice the difference between a sine and a cosine unless you're syncing properly. So in general, you just see the amplitude of the signal coming out, and you know that it's been phase shifted, but you have to pay closer attention if it's sine versus cosine or some angle in between. Okay, one of the homework problems deals with the idea of impulse invariant design, and this is sort of an early introduction to digital filter design, which you'll get to do digital filter design in the project for sure, but we don't really spend a lot of time in digital filter design in this class for a couple of reasons. Number one, there's too many other things to do. Number two, I always have spent more time on it in the real-time DSP class, which is the 3-credit version of what is ECE 4680, the lab. So I spend more time on it in that class, and that would generally be in the spring. That class is terminated now. even though Professor Teekamp wanted to take it over. He can't take it over because he doesn't have a doctorate, so he can't teach it to graduate students. I'm disappointed that there's nobody to take it over, but I have to worry about my own things. It may happen or it may not happen. But if you wanted to learn more about filter design, though, I'm going to quickly let you know that there's plenty of opportunities for that to go learn more about it over here. There's a whole chapter of notes that I wrote originally for an undergraduate version of ECE 5650. It's a good check of my memory. I've been doing this for such a long time. There used to be a class called ECE 4640, and it was DSP for undergraduates only, and then 5650 was for graduate students only. And then when we had issues with enrollment, and it's nothing new, we're having enrollment issues right now in our department relative to the rest of the college, we had to fold both classes in together. So originally I taught the undergraduate DSP class all the time, and these were the notes that I had developed for that class. But all the details in these sections of the notes take you through the filter design from square zero, meaning the polynomials and everything, and lead you all the way through the design from polynomials, of whether it be a Chebyshev, a Butterworth, elliptical, and so on type of filter. And all the design equations are in here, but nowadays we have tools to do that. We have what's available in MATLAB, you have what's available in SciPy.signal, and then my wrapped versions and additional things that I have in Scikit DSP.com allow you to design filters very conveniently without having to go through all the nitty-gritty details of the polynomials and remapping from low pass to high pass, to band pass, and so on and so forth. Just don't spend the time, or don't take the time to do it that way anymore. It's kind of a historical thing now. I don't really feel bad about it though myself. It's like you can't do everything. There's just not enough time. And you will be seeing this throughout your entire career, actually. I call it the idea that you have to abstract things. We have to go to a higher level of abstraction, seemingly, in almost everything that we do. So I got too many things in the way of my browser window right now to find my way back. You don't see what I'm seeing, but I'm seeing all the stuff from Zoom in the way. So I'm not going to jump back to the notebook right now. I'm just going to go say, what is impulse invariant design? It's one of the types of digital filter design. It's probably the earliest one that came along before my time as an engineer. Is I have a continuous time system, and I'd like to build a discrete time system that mimics that continuous time system. So how can I do that? I have this analog filter, and I want to make something to put down below here that will behave in a way that's reasonable. So impulse invariant design just says, I know what the impulse response is here. Let's try to make the impulse responses match. So that's all there is to it. And you come up with saying, I want to make h of e to the j omega match the sampled version of the continuous time signal. And if we go through the Fourier math part of it, we just see that that's all we have to do is make the discrete time signal's impulse response match the continuous time signal's impulse response, sampled with sample spacing cap t. And in the frequency domain, we've already learned that that means that the frequency response of our digital filter is going to be the frequency response of the analog filter when we throw up all the spectral translates to make it look like it has a periodic spectrum, which we know is a property from chapter 2 of discrete time systems. They always have a periodic spectrum. And then additional factor that can get thrown up there is to put in an extra gain factor because of what sampling does. So that gets thrown on there typically too. So one of the homework problems, and I'm going to just tell you which one that is. It's problem 2, text 4.6. is exactly taking a first order low pass filter in the analog domain like an RC low pass filter and sampling it, and that's what this example here in the notes does also. So there's a lot of parallels between this example 4.4 here in the notes and homework problem 4.6. So take a look at this when you're looking at that problem. I do more in the notes than the homework problem has you do, but the idea is to start off in this example with a first order low pass filter, look at it in the Laplace domain, inverse transform it to get its impulse response, and then sample it, and then take the Z transform of this impulse response, and we get this for H of Z, and then we can also get the frequency response for the filter. I did this ages ago in MATLAB. I could do it in, I have done and will do it in Python as needed. And this was actually done in Python. It looks like I rewrote this example rather recently. I don't remember when it was though. But one of the fundamental problems of all of the impulse invariant design goes right back to this equation right here. I'm just going to try to squeeze some space in right here to do some drawing. So if my analog filter is a low pass filter like that, didn't really want to do that. So now I end up sampling it, and what happens is I sample it and I get translates of that signal. This would be Fs 0 minus Fs. And that's what the blue box equation is showing you. If you make the sampling rate really large, or cap T really, really small, you can get those translates to move out of the way, effectively move up and down so they're not touching the translate of interest. But that takes increasing the sampling rate a lot for the first order filter, because the first order filter doesn't roll off very fast. So you have an immediate aliasing problem with impulse invariant design, and that's what this picture is showing. And this is the math of it. This is the frequency response right in here. Unless you make T really small, you end up getting the aliasing, and that's what happens if you say put the cutoff frequency at 0.1 kilohertz and the sampling rate at 10 kilohertz. Your first image comes back at 10 kilohertz, but it's already starting to cause deviation when you get down between 20 and 40 dB down in your low pass filter. And if you get lazy and decide, I'm just going to set the sampling rate or the cutoff frequency at 5 kilohertz and look what's going on at the folding frequency. I essentially don't have a filter at all. It's just dipping down a tiny little bit due to all the aliasing that's taking place. So you have to be really careful, and impulse invariant designs are good because they match the impulse response of the analog prototype, but you have to have a spectrum that's, or frequency response that's band limited. Control systems people will end up liking this because it preserves the integrity of the impulse response, but they might sample at a very, very high rate relative to the bandwidth of the system's time constants. In comms and DSP, it's generally not acceptable to do something like that. Any comments or questions on that? And you'll get, I'm not going to say a whole lot more because you have a homework problem that relates to that kind of leads you through it, and then you can refer to what I have in the notes to see even more of it. It's a pretty simple problem, but it takes into account a really practical example of an RC low-pass filter and what is the digital equivalent of that filter. I didn't really drive that home probably hard enough here, but it's a difference equation that we've seen before. There it is right there. That says if we want to have an impulse response that takes this form, then that's like an RC low-pass filter, and we know what the difference equation for that is because that's basically of this form to within a scaling factor. If you can follow that, I mean, that's what we have to do, is we just have to say a to the n corresponds to e to the minus 2 pi f3t n. So a is e to the minus 2 pi f3t. So it just takes your standard first order difference equation that we played with for a very long time and replace a by e to the minus 2 pi f3t, where f3 would be the 3 dB frequency of the RC low-pass filter, and t is the sample spacing. In a lot of ways it's very cool though, because it says that a first order difference equation corresponds to an RC low-pass filter, which we kind of thought was true anyway. Well, the next thing in here is continuous time processing of discrete time signals, which seems really, really silly. It's like, why would we want to take and jump out of a discrete time system, do some analog processing, and then jump back in again? You could look at it more abstractly and back away and say that that might occur in a system, in the big picture view of a system, but I look at it more closely and say it's just to look at some interesting things that can happen there. And the only real practical example that I have is we could use an analog system to get a non-integer delay. And that's about the only example that I could come up with, is where it kind of might make sense, where you want to get an analog delay. But we can form any type of delay we want all digitally if we want to do such a thing. And it's simplest to just think of a half sample delay that you can do with a moving average filter, and that's an example that's talked about right in here. But I have another function that's available over here. I'm just going to go scikit DSP com and look at digital com module. I've got a function in here which is particularly useful for this and can be used for modeling and satellite communications and other things. I've just got to go down near the bottom here and find it. It's called time delay is what I'm looking at. I was thinking it was near the bottom. Could be wrong on that. Of course, I'm supposed to be able to search. Okay, I found it that way. So it is in here in digital comm module. So the function time delay uses what's known as a Lagrange interpolator, and an efficient structure was in a paper published in 1988, continuously variable digital delay element. And this function is very, very handy because you can put an input in, you can say what the delay needs to be, so you can delay a half sample, a quarter, an eighth, whatever, and then you provide a buffer so that you can buffer more samples in there in your simulation or for your analysis. But this function takes it even further, and it says you can make the delay a function of time if you want to. So the delay doesn't have to be fixed, it can actually be changing with time, which for those of you taking the lab, you're going to be exploring this starting in lab 4, and then you wrap around to this in lab 6, where you're actually making a variable time delay. You first implement a GUI slider to change the time delay manually while the code's running, but then you can automate that and have a function change it. So in SATCOM, you might have signals or satellites that are coming and going, or you might be modeling the passage of a aircraft overhead, and you're talking with that aircraft or that satellite, and the time delay is changing because the distance is changing. So it's pretty handy function. I've used it to implement Doppler on audio and Doppler and other things too. It'll do the job for you with an interpolator that makes delay as a function of time. Does that make anybody think of something interesting? Or I'm just curious if that seems intriguing. Okay. At any rate, so I was trying, when I first wrote my notes, I was learning the book, and I was trying to figure out why did they want to do that. So that's kind of lame in that part of the notes. We're going to move now into a really important topic, changing the sampling rate of a signal. So the book starts off by just saying, okay, we've sampled a signal with sample spacing t. Maybe we want to change the sample spacing later after we have those samples in hand. So we're going to maybe change it to t prime. And a nice example is when t over t prime is rational, so we do a rational rate change. And let's just think of one example. What do those numbers mean to any of you? 44.1 and 48. You think of, we've run into that before. Think about digital audio, and when you're streaming audio, what are two really popular sampling rates that are out there? Compact disc started in 1976 time frame. It established a sampling rate of 44.1 kilosamples per second. And then later, as the industry moved forward and technology moved forward very, very rapidly, the 44.1 is now pretty much been replaced by 48. But compact discs haven't changed. You know, the standard was 44.1, and that's what it was, and that's what it still is. So if we want to take digital audio off of a 44.1 CD and play it at 48, we have to do a rate change. So we have to have a rational rate change. So that's 441 over 480. So that's one application for it, and there's a lot of other applications for those ideas too. But you're too young to appreciate the compact disc, but there is a story. I don't know if I ever told my story, but I have a book on digital audio history that it took place during my lifetime, but it's now it's history. 44.1 was supposedly arrived at by Philips and Sony because they wanted to have Beethoven's Fifth fit on a compact disc when played at a particular tempo by an orchestra somewhere, and they knew how many bits per sample they needed to do stereo. We'll talk about this a little bit more later, but in order to get it to fit, they had to get the sampling rate down a little bit lower so they would have enough storage to store that symphony on a CD. That supposedly is the reason why 44.1 was arrived at. Does anybody know anything different than that, or has anybody heard that story before? Okay. It's interesting though, right? Why would something happen? Well, executives at these technology companies insisted that something be possible for the launch of digital audio. So getting back to the topic of rate changing, the first type of rate changing we're going to do is rate reduction, sampling rate reduction. And I know one of the things that probably ran through your head in the very beginning was when I said later find more appropriate. Why would you think that's acceptable? I mean, my first reaction would be, you dummy, if you knew you didn't want to have it sampled at that rate to begin with, why didn't you do it right the first time? Does that anybody think about that? I know I do. It's like, give me the data the way I need it, and if that's what you wanted to collect to give me, why didn't you do it right the first time? But there's more to the stories than that. So the rate changing now is, the first one is downsampling. So downsampling just says we're going to put this factor of M in there. So we're going to reduce the sampling rate by a factor of M. And the block diagram for the downsampler is the down arrow with an integer next to it, M. So that's downsampling by factor of M. And right now we're not talking about any pre-filtering, but in general, to avoid aliasing, you would have to provide a pre-filter before you decimate otherwise, or downsample, otherwise you would end up introducing aliasing. So that's the other piece to this that we haven't gotten to yet, the need to put a filter in front of the downsampler. And those two together form what's called the decimation operation in digital signal processing. So to understand how this works, we have to think about the spectra and understand what's going on with the spectra when we go through the downsampler. So we have X sub D is the downsample and X sub N is the input signal. And what we want to do is go after the spectrum of the downsampled signal. So we're going to be replacing, we're going to be using cap T now to denote the new sample spacing, but cap T, T prime is just M times the original T, so those substitutions can be made, and we still have replicas of the original input signal when we go and downsample by a factor of M, but now things lie closer together because of the fact that we're downsampling. If we were sampling at 10 kilohertz and now we're going to only sample at 5 kilohertz, the spectral images will be spaced every 5 kilohertz rather than every 10 kilohertz. So the real question is, how do we get the detailed math model. What we have right here in the blue box is what that output spectrum is in terms of the analog input spectrum, but we don't want that. What we want is we want to know we want to relate those two directly. We don't want to have this analog signal spectrum between them be what we have to think about. We just want to know how the two are related to each other. And that's what this bullet is going after right here. We want to relate those two together so you can re-index the sum and do a change of variables, and then we can get, and I'm skipping over some of the details, then you can get this result in this blue boxed equation. And I'm going to try to justify this in a much simpler way without the math hopefully getting in the way. So let's just think about what this equation says. It says the downsampled signal is the non-downsampled signal with the argument now containing replicas at m different locations, and then it has this translation that omega gets replaced by omega over m. Then there's another interpretation where you can take those copies and lay them all out if you want to look at it that way. But to me, the biggest thing is understanding, well, actually two things. In the discrete time domain, the spectrum is always periodic. So whether you sample or downsample, you're always going to have a spectrum that's periodic, and the periods are always multiples of 2 pi. That's guaranteed. But when we go in and replace omega by omega over m, what is that doing? Well, that's changing the rate at which the spectrum rolls out. And I like to think of it as you've got the image. I'm going to go back to something that hopefully can catch in your brain, and that is that you have an ink roller that has an image stored on this ink roller, and if you roll the ink roller over a sheet of paper, and it travels one time around, it will plot the picture of whatever is on that roller. And if you let the roller roll out again, it will plot the same image again, and each time it rolls, it'll plot another image, like a spectral image. But now what m is doing is it's changing the rate at which the roller turns. So if we replace omega by omega over m, it takes m times as many motion in that roller. It has to go around effectively m times to get one period to roll out, because of the fact that m is in the denominator and it's a positive integer. So it rolls out much more slowly when the downsampler is present. So what that means is it stretches things out on the axes. It takes longer for the same image to roll out with m greater than 1. The best way to see how this stretching action is taking place is to go through an example. So I'm going to go through an example right now. This is just m is equal to 2. And I've got the original analog signal coming in. It gets sampled. It gets its images at multiples of 2 pi. And now what we're going to do is draw the spectrum and the omega axes right here. And we're going to make some notes. We're going to just, for simplicity, assume that omega n is pi over 2. And now we're going to downsample. So this as we go from this upper plot to this lower plot, we're downsampling by a factor of 2. So that means things take twice as long to roll out. So the point pi over 2, which is right here, I try to use colors the best I can. That point right there gets stretched out to be pi because we have omega over 2 in the argument of our function. So it's got to travel twice as much distance on the new axes, which is this guy over here, to roll it out. And similarly, if we look at where this is, the same thing's going to happen there. And that is going to also stretch as it rolls out, coming from the higher frequency though, because it's spectral images and it has to be periodic. So it's rolled out at pi as well, the 3 pi over 2. See, I draw that right? Not 3 pi over 2. Yeah, 3 pi over 2. And then 4 pi over 2 is 2 pi. So the stretching action works in both directions. It just takes longer for it to roll out. And that is how the aliasing gets introduced, because now it rolls out more slowly and it stretches and overlaps. So that's what we're seeing taking place there. And then because of the downsampling operation, there's also a scale factor in the amplitude. You have to take that into account when you draw your pictures in the homework problems. And the easiest way to remember that is to think about the fact that if I'm throwing away every other sample, which is what I'm doing when I downsample by 2, the amplitude's going to be half because I'm losing energy by removing samples. So in terms of the new sampling rate, if I want to take this back to the analog domain now, everything is going to be okay in this case because I didn't pick anything where aliasing is going to occur. Things are just now tighter together. And this would, putting a check there to say, I would have been okay with this signal if I would have sampled it at half the rate to begin with, because the signal was band limited and I end up just touching right in here, but no aliasing yet. It's just on the verge of aliasing. The next example, well, I allude to here the fact that to avoid aliasing, we have to ensure that the signal is band limited. In this case, we were safe, but in reality, the signal has to be band limited to omega n less than pi over m. So the cutoff frequency of any filter, of a filter placed in front of the downsampler, should be pi over m. And that's this picture right here. So that just helps us avoid, or ensures that we don't have aliasing. So let's just take this example we just did, and now going to increase m to 3. And if I increase m to 3, now it stretches further. This pi over 2 stretches by a factor of 3 now, so that's 3 pi over 2. And this point right here stretches by a factor of 3, so that ends up at pi over 2 when it stretches down. And we have aliasing. So we have to include an anti-aliasing filter if you want to avoid the aliasing. So we take the signal and band limit it to pi over m. And that means we're clipping off the edges of the original triangle-shaped spectrum. It gets sampled, and now this this is where the downsampler takes place. You know, this upper stage here is the low-pass filter. But at any rate, now it stretches. So this point has been band limited to pi over 3. We decimate or downsample by 3, and it's right there. So everything is working out cool and correct without any aliasing. I know you're going to have to think about this. You're going to have to draw some pictures. The math is good, and I like the math. The thing that's kind of driving this, though, is we have e to the j. Omega is getting replaced by e to the j, the omega over m. So the omega over n makes things roll out more slowly, but we still have the images present because we have to have a periodic spectrum when we get done. So we have those two things coming together, and that is what is tricky about the math here. That's this equation right over here. Just cleaned it up again. Oops. We have the omega over m, which makes it roll out slower, but then we have images, which is what these translates represent. So that's those two things together force the need for the anti-aliasing filter when we do the downsampling. And there are homework problems relating to this. I don't have a specific example over here in Jupyter, I don't think. Time varying delay, yeah, I went through that. I talked about that, and I have an example of that in here. Then I guess I have some comments on the project. I forgot that those are sitting in here. They're in here though, so maybe I should stop lecturing on the chapter and go over to project. I know some of you started to work on it. Does anybody have any questions on the project right now? I'm looking at my watch, and we still have a bunch of lecture time left. I'm just wanting to have an idea whether I should jump over and give any talk about the project. Remember, I told you before you took the exam that you would now be focusing in parallel on homeworks and the project. And that's why you've got more time on this homework assignment. Don't think that you just, oh, I get more time to do the homework. No, you've got to be thinking about the project too. So just be mindful is what I'm saying. You got to do a little bit of both. Okay, so I'm not hearing anybody say anything. I'll just go back over and move on to the next step in multi-rate sampling theory. So we've just come through downsampling, and then we put the filter together with the downsampler. We have the decimator, as it's called. So this is formally decimation. And that means we've got the filter in front and the downsampler. What you do in the project is you do a polyphase decimator, and you're going to find out that Julia's polyphase decimator is very, very fast, which is one of the reasons why I decided to rewrite that part of my project, because I want you to go away from this class saying this new simulation language, Julia, has got some definitely nice features to it, and I was very impressed. I had to spend the time delving into it myself, but I wanted to learn these things, and it's fast for polyphase. And I can't tell you about polyphase enough right now, but we'll learn more about it in this chapter. So the other side of this, if we go down, we might want to go up in sampling. So we have increasing the sampling rate by an integer factor, and the letter L is used there. So the arrow points up, and it says L. So this is upsampling by L. And upsampling is then generally followed by an interpolation filter, and that's a low-pass filter. So the textbook calls the upsampler an expander. An expander is like taking the time axis and expanding it. So we had integer samples spaced at 0, 1, 2, 3, 4. When we upsample by L, we're going to put in L minus 1 samples between every original input sample. And I think I have a picture of that, yeah, right here. So here's an example where a signal was coming along. these two signals here are not the same. This is an interpolation filter, but this shows well the idea of how upsampling works. I'm going to upsample with L equals 5, so I have L minus 1, or 4 samples, stuck in between every input sample. And then in order to form values at these new sample values where I've upsampled, I have to put in an interpolator, and this is an example of a filter impulse response that does what's called linear interpolation, something you learned about in K through 12, right? How do I form values between two data points, like the black ones? The linear interpolator just fills in the value that lies on the line connecting the two data points. So that's kind of cool. So that takes 2 blocks to do that. Again, it would take, in the notation here that we were just looking at, it would take the upsampler or the expander, and then it would be followed by a filter that would average values in between where the zeros were stuffed. So the idea of the expander or the upsampler is to just put values for every L samples. There's L minus 1 samples of 0 that are stuffed in between, and in the book's notation here, they ensure that that happens by putting in delta of n minus kl. So the delta function only fires every L samples, and it grabs one of the inputs, and then it puts out 0 samples in between. So how can we look at the spectrum of the expanded signal? This actually, it turns out in my mind to be easier to understand than the downsampler. So we put in the expression for the expander inside, and then take the discrete time Fourier transform of that together, and the delta function there simplifies the double sum down to a single sum, because it only fires when k is equal to a multiple of L. So we end up with the original input samples, and then we have omega gets replaced by omega L. So what's happening is we're taking our original spectrum and we're replacing omega by omega times L, and this is the opposite of what was going on with the downsampler. The downsampler rolled out at a slower rate. It took m revolutions, so to speak, to roll out one full cycle of the original input spectrum. Now with the upsampler, it's the opposite. It rolls out L times as fast, so it's going to roll out L copies of the original input spectrum in one cycle. So let's take an example of that, and the example of that would be to start off again with a triangular shaped spectrum, sample it, and now we're going to take this signal and we're going to see, I've got L is equal to 2. So I take the spectrum at the bottom of page 36, and then I upsample it by a factor of 2 to get the spectrum of the upsampled signal. And what's going to happen is everything now takes place twice as fast. So if L is equal to 2, this point here now comes along and hits at pi over 2. It's going to roll out twice as fast because there's a 2 in the numerator of e to the j omega. So it's e to the j 2 omega. So it rolls out twice as fast. It reaches that minimum at pi over 2, and then it comes back up again at pi. It just in simple terms, and I didn't write that really well because I'm not holding my stylus too nicely. Let me try that again. Of course, my stylus is responding slowly because I'm running zoom and I'm running my recorder. What I'm trying to say here is when L is equal to 2, there's 2 copies of the spectrum created on the interval 0 to 2 pi. So what you should see in this spectrum down below here is you're seeing that there's 2 full copies of the original spectrum as we're starting 2 pi. If I was to count it in that sense, I'm seeing 2 cycles, but I have to go down, and then up again. That makes for 2 complete cycles of the spectrum is now pressed into L is pressed in the interval 0 to 2 pi. And if L was equal to 10, there'd be 10, and so on and so forth. I might actually have a nice example of that over here in yeah, I do have an example of that in here. There's the upsampling operation, and if I was to pick a different spectral shape for that, I could see more spectra if I wanted to. Trying to see, do I have a nice picture of that? I don't remember what I have in here because I haven't played with this for a year. So I design an interpolation filter right here. So I just designed an interpolation filter. And I'm missing something in here. F was probably defined somewhere else. My throat is starting to get itchy again, so fortunately I'm getting about out of time. I probably didn't really want to do it that way. I was going to try to run an example that would be interesting. I don't have one right here handy though. I have to make one up. Safe to say though is you are going to get a chance to do some things in Python. The first problem is the one that's based on things you already know. Second problem is this one right here. So you are going to be doing some simulations and modeling with this type of a setup. So you're going to be doing downsampling, upsampling by 4, and then you're going to have a reconstruction or interpolation filter running out over here at the end. So I'd have you do a lot of looking around in the frequency domain and in the time domain at what's going on. Why am I having you do that? It's because the only way to really understand what's going on with this stuff is to actually go in and do it. If you just look at the math, it doesn't sink in as powerfully as seeing it in action on the computer. So at any rate, I could show the copies here, and I'm electing not to do that unless you want me to do that as soon as I get done with this example. So here I do show the interpolation filter, and what the interpolation filter is going to do, I didn't talk about it yet, but the interpolation filter has to have a cutoff frequency of pi over L, just like in the downsampling we need to have an anti-aliasing filter of pi over M. So the interpolation low-pass filter should cut off at pi over L. And if it does that, it's able to remove that image, and then we get the picture down below here, which looks all well and fine. It looks like we increased the sampling rate by a factor of 2, as if we never skipped a heartbeat. I mean, we never lost any information. We just now it now looks like our signal was sampled at twice the sampling rate that we started sampling it with. Small typo in here, I'm just noticing. Here I just talk about what the ideal interpolation filter is. It's a sinc function again, but that's a non-causal filter, so you have to have something that's realizable. I'm talking about linear interpolation, which we already looked at. Linear interpolation is realizable. It was this example we already looked at. Compare the linear interpolator to the sinc function interpolator, and we see not nearly as good a performance though. The brick wall interpolation filter, is perfectly flat in here, whereas the linear interpolator is rolling off the amplitude up to the band edge of pi over 5, and then it lets some spectral leakage through after that. So realizable filters have trade-offs, but you have to go with something that's realizable. It's just the way it is. Okay, you can put these two things together, and then we can go rational number rate changing, and that's what this block diagram is. It says interpolate first, decimate second. That way you can merge the two filters together that you need. One is the interpolation, the other is the anti-aliasing, so that can get you a rational number rate change. And then I've got a series of examples in here, and it's making me think of even more examples that I don't have up here yet. Let me just think if I should have that in here though. There was a nice article, yeah. This is from a magazine that used to be available for design engineers. It was called Communication System Design. And it had this picture of, it was talking about decimation and interpolation. So here's a picture of interpolation. Here's our original signal. It has this spectrum. Upsample it by some factor. We stuff the zeros in. We get all the spectral images. We filter the signal though to interpolate, and then all the images go away. Here's the decimation operation. Original signal comes along, has this spectrum. We filter this signal to make sure that it's band limited, in this case, to 2 megahertz, because all of this information up here will fold around and create aliasing. So now we come along and decimate this signal, and it stretches the spectrum back up again. Or effectively, it looks like it's stretching it back up, and we're good to go. This talks about rate changing, whereas if you need to rate change a lot of samples, by a large factor of rate change, in this case, upsample by 12, and then followed by a low-pass filter, it can accumulate a lot of processing steps. In this case, 4.5 mega instructions per second is required if you choose to upsample by 2, by 2, and by 3, so that gets you the same 12, you can get by with less instructions per second to do that operation. The most efficient, though, is the polyphase, which we'll come back and talk about polyphase a little bit later, but that's the other part of these pictures that are in here. You can see that I do like pictures over all the math. If I can get a point across with something memorable, and math can be memorable, but pictures can be more memorable. So I don't know if anybody's thinking that way right now, but I definitely like it. So a couple of examples that I can do, or I can talk about the project. I'll just give you the highlight of the examples. This is compact disc digital audio, and when it came out, they made some enhancements almost immediately because the technology was advancing very, very quickly. So that's a pretty cool example. This is a software-defined radio example called IF sampling, which is also very cool. It talks about how you can build your receiver. This example was built around third generation cellular, and it just talks about doing the IF sampling, doing the undersampling that I showed you the picture of in the animation, and how that worked here in Colorado Springs when Quest, which doesn't exist anymore, but when they owned the Block E receive band for CDMA that runs in this frequency range, and how we could set up a receiver, which would be like in the handset of a cell phone at that time, and take advantage of some great processing efficiencies that come out of IF sampling. So I can go through these, not completely, but I can at least go through one of them, or I can talk more about the project or anything else that you want to know about before we're done for the day. I should be quitting early because we didn't take a break too. So what's your choices? I'm going to open up so I can see it, who's still on. Some of you may have even gotten off already. Everybody's still here that came on today. Anybody got anything you want to talk about? Nothing? Well, one of the things you should be learning from going through sampling theory is it's more visual, maybe not quite as much math, and it's very practical. It's one of the most practical parts of this whole class, is to be able to understand how sampling theory enters a design and stays with it from the beginning to the end, and how you might change sampling rates up and down to make things more efficient for your processing chain. I only have this laptop here, but if I had my other Windows 11 where I'm running GNU Radio Companion, I could show you things in that where I plug into my SDRs. And since I'm sitting here with all my toys around me at home, I'll just show you a quick example of one of the radios that I've been playing with on and off when I get time. There's one of the antennas. This is a Lime SDR Mini, so those two SMA connectors you see on the end, one is transmit, the other is receive, and then the USB is right here. And I can transmit and receive with this device. I've got another device sitting here too, but this one has been kind of a favorite of mine because it's very small and compact. Nobody's saying anything. If you don't want me to go away instantly, though, I will go through at least this example, because this, I mean, does any of you not listen to music, streaming or otherwise? So this idea came about, like I said, shortly after, around 1976, and a little ways after that. People said, "Oh, we're sampling at 44.1 when we have to reconstruct so that the user can have quality sound and not have a lot of high frequency content and not remove anything." People first noticed that folding frequencies at 22.05, we'd like to preserve flatness in this band in here. If we have to reconstruct, though, we're going to have the zero order hold, which is inherent in a D to A converter, and it's going to start rolling off the high end a little bit, and then it's going to let through some of the higher frequency components. So we need more filtering on there, but in particular, their concern was this frequency droop, as it's called, from the zero order hold of the D to A converter. So what people came up with was we can just upsample by a factor of 4 before we leave the audio converter, and if we upsample by a factor of 4, we can remove the spectral translates with the digital filter, and then our first spectral image that we have to get rid of is up at 176 kilohertz, way above hearing. And a very simple analog filter can just roll that, well, the zero order hold of the D to A does this all by itself, and then getting rid of that is not really a problem with a nice RC low pass filter. So this was the beginning of multi-rate processing showing up in digital audio in our commercial products, and these were the compact disc players that the people were buying to play CDs. You would get your music on a CD rather than an LP, a vinyl record. And of course, you know, we're all beyond that now, that nobody buys CDs anymore. They buy from iTunes Store. They buy the digital information directly from the internet. But it's still been the process that we've been through. I think it's time to sign off. I've taken a lot of your time. I've taken a lot of my own time. The cough drop is helping me stay alive, though. So I'm going to go back to my big view. I'm going to stop sharing. And I can see Caleb and Ryan, you're the only two that are left right now. Do you guys have any questions?
So actually, just kind of going to the original CD. And this is really just more informational because I'm curious. But did the original CD players that you would, and I could actually turn my camera on real quick too. Here, sorry about that.
That's okay.
See if that's working. There we go. Did the original CD players actually come with the upsampling?
Yeah, they did.
Yeah. That's interesting. I would have assumed that would have been a technological limitation.
Well, here's the thing, and I guess for you guys that are still on, there's more. Yeah, there's maybe more people on still. I'm just not seeing all of them. The limitation was that building a 16-bit analog to digital converter, which is what was needed to support the CD, right? And that's 2 to the 16th levels of amplitude resolution. That was expensive, and running that at a clock rate of 44.1 kilosamples per second creates a throughput of megasamples per second to, you know, streaming off of the compact disc as it spins around. That was for sure a limitation. So the idea that you would build a D to A converter that would have to run at 4 times that was like, wow, we're going to have a lot of info flowing off that CD. I mean, not off the CD, but in the internal processing. But yeah, that's what was available. I mean, the people that made the analog ICs and could build the A to D converter or D to A converters figured out how to do that. And then shortly after that, we came up with the Sigma Delta converter technologies, which we'll talk about later in this chapter, that kind of, you know, replace this too. This was like an intermediate step. The upsampling by a factor of 4. But the idea is that the analog reconstruction filter can be very, very simple, and that means what people like Sony and others, I bought my compact disc player, first one at Radio Shack, it had that capability already inside it. What they would put on the label, they would say featuring 4x oversampling technology. They would say something like that, like we've got the cool stuff. So,
Right.
but then that got, then it was multi-bit, sigma delta and all this stuff. All this stuff is, it's cool to be a little bit of historian, because if you're in radio is the same way. I mean, still though, it's nice to understand all these things that happened over the short period of time.
No, absolutely. Frankly, I was all surprised that well, with the advent of other disc technologies, that something higher quality than CDs never actually caught on in industry. It kind of jumped over. Well, actually, I feel like we took a major step backwards when MP3s became the common means for everyone getting their music.
Because of the lossy compression.
Yeah, the quality's horrible. It just sounds awful. And I think the first thing that most of those compression algorithms did is they schwacked everything over 16K off, just right off the bat.
And it's a nonlinear thing too. I mean, I listen to Sirius XM in my car, and Sirius XM uses compression, and depending upon what satellite channel, I mean, which program channel you want to be on. I listen to classical and jazz, and I feel like they maintain better quality, but they still have to have their total throughput out of the satellite is only so many bits per second per hertz of bandwidth. So I feel like, voice-only programs don't get the same quality that symphony orchestra music does, because they have to manage their resources in terms of money. We just have a throughput issue. You don't get bandwidth for free, but yeah. It is very interesting to me too, because what you say, I didn't like that either, which is why I continued to buy CDs for a long time.
Mm-hmm. Yeah, and actually going over to the video side of things, I think it just comes down to what the average consumer tracks as basically an important metric. They're not necessarily listening to it. They don't necessarily all have the ear to appreciate that maybe an MP3 isn't as good as the CD that they were using previously. It's more convenient because they've got it right there on their device, and it's the new cool thing. And I'd say on the video side of things, 4K content is definitely the thing now, and it's interesting because I've been following some of the development that Netflix is basically been pushing regarding their compression algorithms to get 4K content squeezed down into fewer bits per second or megabits per second than they were previously sending out 1080 progressive scan. But it's interesting because if I actually look at just say directly from a Blu-ray, the same content, 4K streamed from Amazon or from Netflix or Disney Plus versus a 1080 progressive scan, just Blu-ray, the Blu-ray still looks better. And I think it really just comes down to, it's like, yeah, you might have 4,000 pixels, but what's the bit depth per pixel? You're sacrificing something ultimately. But people care about 4K. That's what they hear, and that's what sells right now, unfortunately. So
yeah, we don't have that in my household. We just have HD.
Yeah.
We're happy. I mean, the TV system that we have is let's see, what's the technology again? The type of screen we have, the plasma. We have a plasma display, and that actually is it's still going strong. It hasn't had any problems with it at all. It seems old-fashioned, but it's just It is just HD. It was the newest thing when we got it, and buying the plasma screen was what I read was a good way to go. And it hasn't failed. It doesn't look washed out. I mean, it doesn't have any of the issues that some of the other display technologies, I think, suffered over time.
Yeah, I had a plasma that I used for several years. Unfortunately, they don't move very well, which is just something I've had to deal with. So by the time we got here, it was about half of it wasn't
I
working
can believe
anymore.
that.
So
yeah,
time to get a new one.
Ours has not
but
moved at all. It's sitting in the same spot. But Okay, I think I think most people have left. I can. I'm going to wrap this up.
Yeah.
And
Ryan just signed off.
what I want to do though is I'm going to sign off. I'm going to stop my recording, and actually I'm going to do that right now.